Hello and welcome back to my computer vision series. Today we will take another look at Vision Transformer, ViT, big backbone model from Google for image recognition. Today we will read the code for PyTorch implementation of it. So this is the plan for today. So first we'll discuss what different types of Vision Transformers in terms of dataset there are. So the original Vision Transformer from Google in the paper that came out in 2021 was trained on GFT dataset, which is internal to Google. It is not public. You cannot access it, which obviously is not really good for the computer vision community because all the previous models, datasets, everything was open, ready for everyone to re-implement if they wanted to. So since then, Meta has created their own version, and then Google published another paper on how to train the same quality of Vision Transformer on open public data. And this is what we'll discuss. Then we will go through the setup for the PyTorch implementation of Vision Transformer for training and inference. So Vision Transformer is a huge model. The biggest one requires something like 5,000 days of TPU training time. So this is not something you can do at home with just a small computer, but we will at least see the training code, what data augmentation techniques were used, how do you load the data, what the data even looks like, and so on. Then we look at the actual model code. Again, this is usually even easier than just trying to understand the algorithm or follow the paper, especially in Vision Transformer case, because the model itself is really, really simple, and we'll see how it works. And finally, we'll discuss some training techniques like learning rate scheduling, weight decay, and so on. Okay, so let's start with the discussion about what model versions there are and where they come from. So let me show you a bunch of papers. So originally, Vision Transformer was proposed in a paper, an image is worth 16 by 16 words. And in there, it was from Google Research, and they basically trained the main version of that on GFT 300M dataset. So this is a giant dataset from Google, not public. So it is only available to you if you actually work for Google. It is roughly 300 times bigger than the famous ImageNet 1K. So it's a giant dataset. And that's roughly 30 terabytes of data. So not something you can just download on your laptop. Then Meta wanted to reproduce something similar. And for that, they used their own dataset called Swag. So if you go to the Torch Hub Vision Transformer page, so Torch Hub is the source for pre-trained weights for most of the models trained in PyTorch. So if we go to like the huge model here, for example, H14, they say that it was trained on the Swag dataset. The Swag dataset, I think it's just Instagram images, to be honest. So basically they call it semi-supervised because they have a bunch of images, not as big as GFT, but maybe twice smaller. And instead of human labeling, they actually used Instagram tags as the signal for the model. And they managed to train their own Vision Transformer on this data and get similar results in terms of quality to this GFT label dataset. And finally, after the initial Vision Transformer paper from Google, they've published another paper. So this is pretty much the same research group called How to Train Your Own ViT. And basically says that what if you don't work at Google and you don't have access to this giant GFT dataset? Well, then you can use a lot of extensive data augmentation to effectively create more data out of existing images. And they managed to reproduce similar results from the big ImageNet 21K dataset. And here they talk about when does that make sense. And long story short, if you just have a lot of data, just use a lot of data. And depending on your model size, you might actually not want any data augmentation. But then if you don't have a lot of data, you can compensate for that by using data augmentation techniques. So coming back to our dataset size, so the original vision transformer was trained on GFT. This is the biggest of them all. The meta version that is probably used in majority of object detection models at the moment, because they all are usually in PyTorch. This one is called Swag, and it's but quite smaller than the ImageNet 21K. So this is the bigger brother of ImageNet 1K with roughly 15 times more pictures and 21K classes. It is still possible to train Vision Transformer of the same quality on this dataset, which is roughly 30 times smaller than GFT, but you compensate for that by using extensive data augmentation. None of these are actually easily available, so you can't just randomly get ImageNet 21K from internet, for example. The only one you can just download readily is ImageNet 1K. And so today we will look at how to train Vision Transformer on this even smaller ImageNet 1K dataset. It will obviously be of slightly worse quality than the original, but at least it allows you to understand like what the training looks like, different parameters for it, and stuff like that. Now let's discuss how to set up debugging of the PyTorch implementation. So original Vision Transformer by Google, they actually open sourced the code, and it is written in Flax. This is not what we are going to read today, partly because although they open sourced the inference code and fine-tuning code, they didn't really explain how to train it. And PyTorch implementation actually has reproducible examples on how to train the model as well. So this is why, and because we know PyTorch better, at least I do, this is why we are focusing on PyTorch implementation today. But we trust that it is both the same in terms of techniques used and in terms of the quality that the model achieved. So first, I'm going to just Google the GitHub for Torch Vision. This is where all of that is stored. So we can quickly validate that this Vision Transformer B16, for example, that it indeed comes from here, right? And then, so yeah, let's do it once again. So we have this torchvision /models/vision transformer.py. So this is the GitHub, the code for the actual model definition. And they actually have a bunch of models here, ResNet, Swin, VDG, and so on. In addition, and that is a lesser known fact, if you go to the root of the repository and then you go to references, they also have training script examples on how to actually train or fine-tune the model. And so in classification, they also have examples and actual parameters used to train for all these models: MobileNet, ResNet, EfficientNet, and the one we need, Vision Transformer. So this one is the one we need. So let's go ahead and just clone the repository. Now we need to install the dependencies. And here is one interesting thing. So if we go back to the training script in train.py, for example. So in here, it imports Torch Vision. And this is usually how we do it, right? So we just install Torch Vision using pip, then import it in our script, and then just use it. However, if you look at where the models are defined, this is actually the Torch Vision module. So this is the source code for the Torch Vision library itself. That is cool, but it might create some complications for us because we actually want to read the source code and we want to be able to step through that in the debugger and maybe modify it a little, insert print statements and so on. For that, it is useful to install this module from GitHub, the Torch Vision, as a module that you have source code for instead of just a PIP dependency. And the instructions on how to do that are present in the repository in the file called contributing.md. So it says that basically if you want to write the code to this repo or if you want to read the code, you have to go through this process of installation, install some dependencies, and the main one here is this Python setup.py develop, which basically compiles the stuff necessary for this repo to work, and then you can just import stuff in your code, in your training code from this repo, debug through it, and all of that. So let's go through this. I'm usually starting with creating a fresh Conda environment just to make sure that whatever it is I'm setting up will not mess with my other projects. So I've created the environment, I'm activating it. Next, I need to find the specific CUDA version that I have. So it is just to help avoid some bugs. So in my case, I'm on a Ubuntu machine, and I have a CUDA version 12.1 installed on the machine itself. So it's better to install PyTorch of the same CUDA version. And this is how to do that using the official instructions from pytorch.org. So I'm just installing using Conda from the special repos, PyTorch and PyTorch CUDA. Then we go through what they tell here in what dependencies are needed for the actual contributing development of the repo. So it's libng, jpeg turbo, and so on. And then I run this setup.py develop. So you might see some CPP compilation warnings, hopefully no errors. That's not a problem. It is installing, it's going to take some time. So in the meantime, let's go ahead and deal with the dataset. So as I was saying before, the ImageNet dataset, although they claim that the entire 21K dataset is actually open to the public, to actually get it, you need to write to them to access it. And I tried to do that roughly half a year ago, still didn't receive any response. So maybe because I'm not really affiliated with any research group or anything, maybe someone will have better luck. But the subset, the 1K subset, is available on Kaggle. So you can just go to Kaggle, click on data, and then just download it all. It is roughly 160 gigabytes, so it will take some time. And this is how it will look like. So on after unpacking everything, you'd have some CSV files with mapping from class to index. Then the main folder is this ILSVRC. So there it has data, it has image sets. We go to data, CLS log. And here we have test, train, and validate sets. If we look at the validation set and just see what happens here, it all is divided into folders where each folder corresponds to the class. So it's not really clear what the class N018 blah 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 actually means. That's why we have these CSV files up top, but that actually tell us the human readable label for the class. So if we go to this one, we will be able to see the actual images. So this is the format of the dataset. There is a PyTorch ImageNet dataset class, I think that's how it's called, that just takes in the pointer to this location of the data and then just loads it for you. So the installation was complete. To check that it is installed correctly, I just go to Python and just try to import Torch Vision. So now if this worked, this means that you have installed this Torch Vision module that you've just compiled. So this is yours now. You can modify it. You can step through that in the debugger. So congratulations. So the next step is to try and launch the actual training and see that it actually happens. So I go to References, Classification, and then I copy the training command from this README file in the root folder. So in here they use torch run. This is a script that allows you to launch it using many GPUs. I don't really need it because I just have one, so I can just go and call python train.py. So the only thing missing in this comment is the actual path to data. So if we go to train.py, look at command line arguments, we'll see that there is this data path that by default assumes that the data is put into /datasets1 ImageNet full size something. So we need to make sure that it points to the dataset that we have downloaded. So here is the full command. I launch it, and let's see if it actually manages to train for a few iterations at least. So I'm setting batch size to just 2 because my GPU is quite small. Otherwise, I'll just run out of memory. And yeah, it is training successfully. So another interesting thing that I do to help me read the code and debug is to try and go over the same script in debugger. So for that, I have my launch.json configuration in VS Code, and then it looks like this. So this one is a typical, but important thing here is to add arguments to the script. And here are the same arguments that we've copied from the repo, everything plus this path to the ImageNet dataset. So I have this launch configuration. I can come back to train.py. I set a breakpoint right in the beginning of the main function, and then just click on the debugger. So it should launch the same script, but now it will stop where I need it to. And I'm actually going to print these arguments because it's really useful to print all of them out and just save it for later use, and you'd see why. Because a lot of them actually have default values, and this main function in many cases just passes around this args object with all the parameters. So we will now create a Jupyter notebook that with the same code. And by doing that, we will be able to actually copy stuff around from this train.py script. And since it refers to args in many cases, we'll need that as well. And that will just help you debug things. So just write down everything here. So now I'm just going to touch sandbox.ipynb. That way, I have now a Jupyter notebook. I'm actually going to use the one I've already written with some helper functions. So here it is. Since I've created this notebook at the same folder as the train.py script, I can now just copy everything from here, which includes imports, including the ones that actually look at this specific repo. And because it's in the same folder, they will just work. So I can just keep copying code around and just see what it does. Then I just have my typical helper functions. So unnormalize changes the normalization because we feed pixels to the network with 0 mean and unit variance, which means some of them will be positive, some will be negative. But then if you actually try to plot that in matplotlib, that looks awful. And if you unnormalize it, you make it look okay again. Then the function to actually plot results. And now this arguments object. So here I just copied everything we've just seen in the debugger. And we create a class that inherits from argparse.namespace. And by using that, we now construct the object called args that can be used in exactly the same way as the command line arguments in train.py script. So we just can keep copying code around and it will still work. And again, yeah, this is just copy paste from train.py. We can see that the data is loaded successfully, and we can see the actual images. So we've gradually approached the point about data loading and augmentations. So now we are about 20 minutes into the video, all the setups, installations, all of that. That was basically to set up the toolbox for debugging. And now we can see why it might be useful. So here we can actually plot not just a random image from the dataset, but actually the input to the model itself. So here we can see that the image that we get is of size 224 by 224. So ViT is trained on fixed size images, similar to ResNet, to be honest. So they are all resized to the same size. If we just keep clicking on this button, fetching the image from the dataset and displaying it, we can see that the image is the same, but augmentations are slightly different at each time. and we get the feel of what these augmentations are. So there is a parameter in the arguments that is called auto augment, and the PyTorch reference says that it should state RA, which stands for random augment. And now we can actually read the code for what that does. So I'm just jumping into this load data method that returns the dataset. And so here we can see that the dataset itself is called dataset Torch Vision datasets image folder, which is the folder that we've seen where you would have a folder for validation images, inside of that folder for each class, and then inside that class, the actual images. And then there is a classification preset that basically controls various augmentation techniques that will be used. And so ours is called RA, random augment. We can just read PyTorch documentation for that. So here it is, the rand augment class. And here they explain at length what different sorts of augmentations there are. And you can see that they roughly correspond to what we've just seen. So padding, pixelation, different sorts of crops, random perspective that rotates the image a little bit and modifies it, flip from left to right. What else? This one is random resize crop, this is a polar one. Grayscale, different color augmentations, in rotation, solarize. So if you just keep clicking on this button here, you would see those once in a while. And this is basically what we're talking about when discussing the paper, how to train your ViT. So we don't have a lot of data. We don't have this Google GFT dataset with 300 million images. So we compensate for that by generating more data, basically, with augmentation techniques that we think are safe, because in reality, in 3D world, you do see objects from different perspectives. You might get color modifications due to lighting, due to how you took a photo, and so on. Next, so this was the dataset. So the dataset basically can load one image for you. We also have a data loader, which iterates over the dataset and then loads a bunch of images. And here is, so this is again just copied from train.py. And here we are using the custom collate function. So collate function is the function that is used to unify several images into one batch. And this mix up cut mix, we can see what it does in just a second. So we had 2 images in the batch, because I just set the batch size to 2. And we can see that one image was sort of added on top of the second image. So we've seen the same technique in, this is the first image in the batch, and then the second image will contain the other half of the dog. We've seen something similar in YOLO v5 training, but now it is using just official PyTorch implementation instead of the custom one for YOLO. So this is basically saying that, hey, we might encounter like just parts of the image. This is like another heavy augmentation that makes the job a bit harder for the model to actually understand what is happening here, but still the model should be able to deal with this. In our case, the batch size was just 2, but actually if you increase it, 8, it will still take 2 random images from the batch and then cut mix them together. So let's just quickly validate that. So now the length of images is 8, but you can still see that only 2 images are mixed together in some sense, and they are always mixed randomly. Sometimes you get like a small version inside a large version. Sometimes you get something different, like 2 of them merged roughly in the same proportions. Sometimes it's even hard to understand what is going on here. Thankfully, it's an actual PyTorch class, so documentation is available. It's pretty well written. Another interesting question is what happens to labels. So in YOLO, that was object detection tasks, so it was perfectly valid to have two objects in an image. So if you just take two images, merge them together, you can still say that, this is one object from the first picture and this is another object from another picture. In our case, we are doing classification. So vanilla ImageNet dataset just had one class label per image. In our case, we can see that labels is now shape 8 by 1000. So basically, instead of one label per image, we get 1000 images. And you can see how they look like, right? So let's go here. So basically, instead of just one label per image, we get this vector of logits. And actually, two of them are non-zero. So it is like saying, I have mixed two images together, and I said that this image now, and the class label is like 50% this, or 50% this, or 90% this, and 10% this, depending on like the ratio of sizes that is taken in by the pictures. So you can print that out like this, x greater than 0. And yeah, you see that two of the class probabilities in the ground truth labels are above 0, and here they are. Now we are finally ready to read the actual model code. I'm coming back to my Jupyter notebook, and now, thanks to all the setup that we did, it is going to be relatively straightforward. So I've loaded my images batch from the data loader. I can just apply the model to that. Let me do that. And yeah, I had 8 images in an input and 1000 classes per image for probabilities output. Now, I want to read the code of this model. So mine is called ViT base 16. I can just search this function, and it is defined in vision transformer.py. So this is the Torch Vision /models module. So in here, it deals with some boring stuff like validating the weights, then calling this vision transformer. And the vision transformer class is the one that actually defines the architecture. So as you can see here, this one is inherited from nn.module, like all the neural networks do. So let's just scroll down to the forward method and just put the breakdown at the very beginning of it. And you can see here that it is just 15 lines of code, basically. So it's a really simple model. So now let's go back to the Jupyter notebook and just press on debug cell. And yep, here we are in this forward method. So first, let's just go through that once on the top level, printing out all the shapes. So input is 8 by 3 by 2 to 4 by 2 to 4. So all the images are going to have the same size. We have 8 of them in the batch. Color dimension is 3. And then this process input basically performs this patching operation. So let me quickly go back to the slide with the model architecture. So in all transformer-based models, the actual transformer is usually exactly the same module, but we need to understand how to form the input to that and how to form the output. So we get an image, we divide that into a non-intersecting patches, then we flatten them out. And usually after doing that, we also want to add some sort of positional embedding. And that is the sequence input to the transformer. We also add this basically constant trainable class token that we just add to the sequence and pass that to the transformer. And so the output of the transformer is always the same shape as the input. And this first token that corresponded to this constant trainable class token is going to be our prediction output. So we take this token, which is itself an embedding, we pass that through some dense layers to get our class probabilities. So let's see what happens here. So I've passed it through the preprocessing. Now it's 8 by 196 by 768. So 768, that's the hidden dimension of our version of ViT. And then 196 is basically 14 by 14, right? So I had 224 image dimension as an input, and I've divided that by 16 by 16 patches. So if you divide 224 by 16, you conveniently get 4 pixels. So I have 16 patches on each side, each with 4 pixels, and that's what we see here. So this is already after flattening. Then we have this class token. Let's just print what that is. So the type of that is an n-dot parameter. So basically, and it's not even randomly initialized, it's initialized with zeros. So it is going to be trainable. So the model will, right now it's just at the beginning of the training, but during training, it will put some information in there, but this information does not depend on the actual image. So it's constant for every image. So we had the shape of X was 8 by 196 by 768. So my sequence length was 196 at this point. Now I'm adding this class token repeated for every batch element, and then just concatenating all of that, which just added 1 token. So I had 196 sequence length, now it's 197. And then I pass that through this encoder model, and you can see here what it is. It is quite long, but basically it's the vision transformer encoder. That's the transformer. The output of that is exactly the same shape as the input. And then we take the first token. So we throw away 196 of them that corresponded to the actual image content, and we focus on this output class token. And then self.heads, that's the dense layers that do the actual classification. Right. So then output of this is 8 by 1000. So we've got 1000 probabilities out, and that's it. So we return now. So I can just go over this once again, but now digging slightly deeper into the network. So let's start with this process input function. It is actually really straightforward. So we get our image as an input. Then we do some assertions and just shape calculations. And then we have this convolution projection. Let's type what it is. That's just conv2d, right? That's really interesting because ViT promised a model without convolutions, but here we see yet another convolution just at the very beginning. So the patching operation, the operation of dividing an image into patches, that's actually a special case of a convolution. So let's see where that is defined. So it is defined as just conv2d, and sometimes conv2d with activation, but it has kernel size being equal to stride, which means that it's not just a convolution that sees the slides along. It's actually just dividing the image into non-intersecting patches. So you apply the convolution, then move it all the way here, and then apply it again. And the output of that is the patching that we get. So this is a special case of convolution. And the important thing to understand here is that the kernel weights used to project this actual colored image into this embedding space, these weights are the same for each patch. So the same kernel is applied here, the same kernel is applied here, here, and so on. So let's come back to our forward method and take a look at the encoder now. So just going to continue until here. So the encoder is also relatively simple. Let me break at the forward method of that. Right. So input.shape is this 197 length sequence. Right. So I move forward. I add the positional embedding, and positional embedding again is just a parameter. right? And the shape of that is the same, so 197 by 768. So note that it is a one-dimensional positional embedding. They talk about that in the paper. Basically, they do not really bother with 2D positional embedding. So we're actually just not letting the positional embedding know that 2D image is being processed. Instead, we just let it learn by itself. And thanks to the fact that in the original paper, at least, there is a lot of data, it just learns successfully that indeed I do have a 2D image, and it's useful to understand the 2D representation of that. So we have this learnable positional embedding, which is initialized with something random. So it's not zeros now, it's just a random normal as far as I can see. Then we add that to the input. We have normalization layer, and the actual layers are defined in this encoder block. So let's break there as well. And this is the actual transformer layer. So I'm pretty sure most of you have seen transformers in PyTorch already. So the main function here is self-attention, multi-head attention in PyTorch. So ln1 is just normalization, layer norm. Then we have self-attention. And we know that this is self-attention because we have our input sequence X that comes from image patches. And we pass that in 3 times to the multi-head attention layer as query, key, and value. So this is called self-attention. Then we have dropout. This plus sign here is basically a residual connection. So we always have one skip connection that actually skips this attention mechanism and connects the output directly to the input as well. And then second layer normalization, multi-layer syncron, another residual connection, and this is pretty much it. So let's come back to Vision Transformer forward method. So we are in the encoder now. We come back to that, and that's it. So we've got our processed sequence of tokens. We get just the first one out. And once again, this special class token that we added as 197th token, it basically allows the network to store some global information that is supposed to be useful for the actual image classification. And this is exactly the same token that we take out conveniently. So then we pass that through some dense layers. Let's take a closer look at them. It's just sequential and heads layer, and the head layer is linear layer, so dense layer, hyperbolic tangent activation, and then another linear layer, and that's it. So as an output, we get 1,000 predictions per image because this is image network A, 1,000 classes. This is pretty much it about the model. So a convenient thing about this PyTorch repo, the Torch Vision, is that it actually has a lot of models here. So this pretty much the same setup will just work for Swin transformer, for example. So you can just swap the model now and read the code for that one conveniently. The processing is the same. The training might be a little bit different, but it's all controlled by the actual arguments. Now let's take a look at some training parameters. So I go to training.py. This is the main function. So here the loss is defined. So we have cross entropy loss, typical for classification problems. Although in our case, that's a bit special. I think we didn't really see it before. Instead of just having one class, we might actually have 2 classes in the image, one being 40% probability, another being 60% probability because of this mix-up, cut-mix data augmentation. Then we have weight decay, and weight decay is actually further customized, and it's different for the class token, for positional embedding, and stuff like that. Then we have optimizer, which in case of Vision Transformer is Adam. So most of the transformer-based models use Adam optimizer. most of convolution-based models tend to use SGD as an optimizer. Then we have learning rate scheduling. And in case of vision transformers, that's cosine annealing learning rate. That's actually an interesting one. Let's just see what it is. So yeah, it looks exactly as it sounds. So it has some cosine function in the annealing schedule, which means that it's basically not decaying down to 0 and that's it. It will actually restart from time to time. So yeah, that I guess is interesting. Then we have warm up, and this is the actual training loop. So we iterate over epochs. We have train one epoch function that iterates over the data loader, puts everything to device, sets 0 grad. This is the gradient scaler, which just multiplies the gradient by some parameter. Then we compute the loss, compute the backprop, and step the gradient. This is pretty much it. But it's good to have the actual recipe. So I think the components here are not really new for people that made it thus far. So learning a scheduling, warm up, weight decay, all of that. However, it is good to have the actual recipe on how to train your own model in case you, I don't know, suddenly participate in a big project like that and you need to actually reproduce it or create your own model. You can use this as a starting point. So big thanks to PyTorch, for taking the time to open source models, to implement models from other frameworks, to publish weights and instructions on how to train. So this is pretty much it for today. I hope it was useful. The setup to be able to install every dependency and actually launch it yourself and read it for yourself and debug it. The explanations from the code. Hopefully, thankfully, the model is really simple. So you can just see how it works in 10 lines of code, basically. In addition, I wanted to say that I have my channel. I have been making a lot of videos about computer vision and object detection specifically. So today we were reading the source code for Vision Transformer. I also have a video about just the Vision Transformer algorithm. The very next one will be about Swin, a different variant of big backbone model transformer based. Also, we've looked at YOLO model, which is, I guess, a classical convolution object detection model, which is really lightweight, rather simple, and because of that, it is still popular because of how easy and fast it is. Then we've looked at the fundamental transformer-based modern proposition called Deter that allows you to do object detection without any handcrafted components like non-maximal suppression and anchor boxes. And then a lot of improvements on top of that, like deformable Deter, deformable attention, Deter with dynamic anchor boxes, denoising Deter. I have videos about all of those, about the algorithms, about reading the actual source code. All of that basically builds up to current 2 state-of-the-art models. So Dino is quite a famous one, which is not state-of-the-art anymore. And then Codeter, which is state-of-the-art right now as of 2024. Both of them are Deter-based, and they are actually written on top of the same code base. So it's really good to go through this entire path of the Deter variants, because all of these concepts are going to be used in Dino and Codeter. So Dino is based on denoising Deter, dynamic anchor boxes, deformable Deter. So I'm hoping to get there quite soon. So see you next time.